Thank you. Feliz Año Nuevo. So, as you can, thank you. Happy New Year. As you can tell from my awful pronunciation, that's the only Spanish I know. So let's go to the real English section. My title is Augmented Compound Urban Temperature Extreme, and the single name is Acute. It means very serious. We need to be very careful about that. And today I'm trying to make an argument, a very simple argument.
Just for the photo.
Oh, okay. A very simple argument that it...
Just a moment.
Here? Oh, okay. Okay, I will continue my argument. My argument is very simple. Is that if we want to understand the future temperature extreme, we need to combine the effect from climate change and also from the stronger urban heat island effect from urban expansion. Okay, that's my argument. And then, first of all, we need to look at that, like, the heat extreme is a very dangerous environmental hazard. If you look at the casualty it caused from in 2003 in Europe, 2010 in Russia. Maybe you don't feel that in Lima because the Mediterranean climate here is extremely comfortable. Like, the temperature didn't kill a lot of people here, but it's very dangerous around the world. We need to take care of that. And according to the temperature record of this year, like the last year just passed, 2016, just blow off all kind of temperature record. It's like about 1 degree Celsius higher than any historical record. And according to the global climate model, like maybe it's very difficult to see here. The whole world will experience about 3 to 5 degrees of warming, especially in the high latitude. But that's not the whole story, because there are two figures. On the left is the intensity of an urban heat island effect. It's the temperature difference between the city and the surrounding area. And on the vertical axis is the temperature. And on the horizontal axis is the population. But be careful, it's the log scale, not the normal scale. So it goes from 10 to 100,000, 10,000, 100,000. Okay. On the right-hand side is the forecast of future urban population growth. If you combine them together, we can see that all the little dots will move to the upper right, and the urban heat island effect will become stronger in the future in all the cities all over the world if we look at this figure. If we combine these two figures. That's my argument. We need to think about the global climate change and the regional urban heat island effect in order to understand what is the real temperature change that we will live in, because most of the people will live in the cities in the future. And so the global climate change is caused by greenhouse gas emission. However, the urban heat island effect is caused by regional, local urban expansion. So there are numbers of forecasts about future climate change, different scenarios about how the temperature will change depending on our economic system, our transportation, production, how much carbon emission we will put into the atmosphere. On the other hand, this SSP is called Shared Socio-Economic Pathway. It's about how our society develop, the economy. It's relatively different from how we, these are just the economic growth and population growth. This scenario will determine how much urban expansion will happen in the future, how big the cities are growing. So if we have to combine these two types of scenarios in order to understand the final consequence of temperature increase in the city. These are just the very early results that I got from in the summer. And if you look at, maybe it's difficult to see from the legend. If the dark red dot represent like about 8 degrees increase, and the orange one represent about 2 degrees, and the green one represent like a decrease of temperature. And you can see like, and the size of the dot, it's proportional to the size of population and the area of the city. Okay, that's the result I got. So I will talk a little bit about how did I generate that result. First of all, I have to do an urban expansion forecast to see which city will grow faster than other cities. And I will use this model. I won't go into too much detail about the model, but basically, the land area of the future urban growth depends on GDP per capita, and also the location of the new urban land depends on the slope, the proximity to major road, and also the original land use, the geographical factors. What's more, we have to also control using the Gibret's law to control which city will grow faster than the other. This one is a very important figure in urban study. It's the relationship between the log of the population and the log of the rank. So basically, it's kind of difficult to understand the figure, but basically, it's like the biggest city will be twice as big as the second biggest city, and about 3 times as big as the third biggest city. So it's also, if you rank all the city and you go from the biggest one to the smallest one, and the size will decrease at a log scale from 100,000 to 10,000 to 1,000, something like that. Okay, so how do we generate that kind of patterns? Is that there's a basic principle, is that the bigger city, they grow faster, just like people. The rich people, they can get more money faster than the poor people. Same for cities. The bigger city, it's very easy for Lima to grow like very fast, but relatively difficult for Tarapoto maybe, Cusco. That's the only 3 cities I know in Peru. Okay, but that's basically the pattern of size and the rank of cities. So these are the forecasts of future urban area. So you can see most of the growth will happen in China, India, and Africa, but not much in South America because the urbanization rate here is already pretty high. It's about 70 to 80% for most of the cities here. And so that's the same distribution I talked about just now, but the blue dots are the current city sizes, and the red dots are the future city sizes. As you can see, they all grow vertically, and again, that's the log scale. So if you combine the same log scale of city size and temperature, you will see that the temperature will grow as the city grows. And but somehow the future city size distribution does not follow the same straight line, because for the very big city, there are some physical constraints. Like some cities are surrounded by mountain, surrounded by river or ocean. It's impossible for them to grow to real big. So that's good for them because the urban heat island effect may not be as serious as the pattern predicted. Okay. And then after we forecast the future sizes of cities, we can build the urban heat island model to predict the future temperature. The urban heat island model depends on a few variables. First of all, the size. The bigger it is, the hotter. And also depends on precipitation. That may be a surprise because for cities in different climates with different precipitation, the surface roughness between the urban area and rural area will be different because you have very different types of vegetation. So with different surface roughness, they will have different efficiency of dissipating the heat. So if the surface is rougher, it's easier for the heat to come out from the surface to cool down the city. So that will change the urban heat island effect. And also how much vegetation you got in the city. If there are more green area in the city, it will be cooler. And also the albedo, albedo just means the reflectance of the surface. How much radiation going into the surface and how much of the portion of the radiation will go out immediately from the surface. Okay, these are just the figures to show the relationship between urban heat island intensity and these variables. And also the location, because at different locations you may have different climate that will change the precipitation. And okay, I used an empirical model here because that's just the early result. I just want to prove that these two factors, climate change and urban heat island effect, they are comparable. They are both important. And these are the 15, that's the R, the correlation coefficient of my model. It's 0.73. It's not very good, but fair enough for the global forecast. And as you can see, most of the errors, that's the distribution of the error. Most of the error fall into like plus and minus 1 degree. So I'm pretty happy with this result. And then I will input the area forecast from the socio-economic pathway. And then I will input the forecast from the global climate model to see how will the precipitation change in the future. And then I will just keep the vegetation and albedo the same as now, because I don't know how the cities will change their vegetation and albedo in the future. And also the location will never change. And then that's the results. As you can see, the blue charts are the temperature distribution of the urban area now. And the red one are the temperature of urban area in the future. And the top figure represents the existing urban area, like here, maybe downtown Lima. And then as Lima grows bigger, even the downtown will become hotter. So that's the change, as you can see, from just 1 to 2 degrees all the way maybe to 4 to 6 degrees of urban heat island. And also on the lower figure will be the new urban area, like all the way out there, their temperature distribution. And these are just comparison. We can travel around the world to see in Malaysia, and on the left will be urban heat island intensity. What will change, like there will be increase of 4 degrees. And on the right, you can see the effect from climate change. The same comparison in Southeast Asia and Colombo and India, Africa and Italy, because there's not much urban expansion happening in South America, so I didn't include any cities here. Sorry. And conclusion and future work. So conclusion is very simple. The same argument, like we need to combine urban expansion and climate change when we want to understand future temperature extreme, heat extreme. However, we have also to look at the intra-urban variation, but because my simple model just treat the city as the same, but somehow like in the downtown area, the temperature will be very different from the surrounding suburban area. That's in the future, I need to figure out how to forecast these differences. And also I will use the physical model to understand the mechanism between the interaction between climate change and urban heat island effect because the rural area and urban area, they will respond very differently to the increase of carbon dioxide concentration. You need to use a physical model to understand the mechanism. So the model is still running, so I didn't include any results yet. And why do you care about like the extra 1 or 2 degree? There's a very important implication from public health. This paper coming out 2 years ago, as you can see, as the temperature increase, this line represents the death rate. There's a non-linear increase of death rate according to temperature. So the additional 1 or 2 degree may double or quadruple the casualties of extreme temperature. That's why to figure out the exact temperature increase is very important. So I think, yeah, that's it. I would like to thank Yale School of Forestry, Yale Graduate School, and also Yale Institute for Biodiversity Studies to support my research. And thank you for being here in the new year. Thank you. Hola.
Am I in English or in Spanish?
English, please. I'm not good at Spanish.
Okay, first of all, my congratulations. I'm very impressed about your content
Thank you.
said to us. But I'm just taking attention about your information all about heat increasing. So I'm just wondering what are the possibilities for the future to prevent or just in this environment. Peru, we are in a land of landscape, rainforest. We need to keep a future, and we don't want it to be destroyed or just polluted. So what are your recommendations? In this case, it depends on our government, I know, but scientifically, explaining what would you say?
Okay. First of all, I'm not an expert on South American cities, so my conclusion, my suggestion may be wrong. So just to make it clear. So I think Peru has a very different problem because all the big cities are in the arid or semi-arid area. So according to the previous research, like the urban heat island effect in this type of climate is not that strong. Because the major factor of urban heat island effect is that if you remove the vegetation, you will change the temperature, the heat exchange between the surface and the atmosphere. But somehow, because there's not much vegetation in Lima, so if you build a city, it won't change that much. But somehow, Lima has a very different problem because there's lack of water here. It's very dry, and in order to, one of the major action you can do to prevent temperature increase in urban area is to grow a lot of vegetation, and that takes a lot of water as well. So how do you manage the balance between spending water and also reducing temperature? I think that's the key issue that people here need to work on. Yeah, but about the forest, actually I'm not an expert in like the forestry study. Although I'm in a forestry school, I study the forest of buildings, not the trees. So I'm afraid that I cannot comment too much about the Amazon forest. Yeah. 谢谢. Please. Hi.
Nice to meet you.
Nice to meet you too.
Happy New Year for all. Well, my question is talking about what is your expectation for the next 20 years about if we are talking about the climate or the temperature, and what would you consider if Lima is a crowded city, and how we could decrease the temperature here in Lima?
Okay. So my expectation. So I will predict that the temperature will continue to rise, but I hope that we can stop it somehow. Yeah, because like the international relationship between all the countries, they are not cooperating very well, and also one of the major leaders, America, they just elected a president that denied climate change. So the future is not looking very well. But for Lima, I think, as I have talked about, that you need to think about the balance between how much water you are willing to spend on vegetation and how much temperature you are you want to decrease. And then after you figure out this trade-off, and then you have decided how much water you can afford to reduce the temperature. And I think then people need to work on this chart, on the public health surface. What kind of surface can you provide to the people so that even though the temperature is very high, you can still reduce mortality? So this chart is not static. This relationship depends on so many other factors, like their income, and also the social relationship between the people. There's a very famous study about the heat wave in Chicago in 1995. They found that the social isolation, it means that you have no friends, no families, then those people will die first, and in a large number. That's very dangerous. So if you can build a society in the way that people can help each other, and then maybe you can survive this temperature increase. That's from a very different perspective. Yeah, after you figure out what can you do physically, and then you need to think about what you need to do socially. I think like South American people are good at that. I mean, you are fantastic. You're very passionate about your friends and families. I believe you will survive that. Yeah.
Thank you.
Thank you so much.